recall that SAT is all the satisfiable Boolean expressions. In other words, SAT is all the Boolean expressions that are not contradictions. 3-SAT is a sub-language of SAT. It's all the satisfiable Boolean expressions in conjunctive normal form, and which means that it's the conjunction of clauses, and each of which has at most 3 terms. Now, let's take this particular example, for example. What would be a satisfying assignment? If I wrote x1 to be true and x2 to be false, then I would have to let x3 be, for example, true, and of course I could let x4 be anything I want because it doesn't play a big role here. So let's see, x2 is true, makes this clause true. x3 being true makes this second clause true, and of course the first clause is true because x1 is true. Here's an example of the simple-minded reduction of SAT to 3-SAT. Suppose, for example, we have a long expression here, and it contains this clause which has 4 terms. Well, one of the things we need to do is to come up with a 3CNF form. We have to replace this clause by a conjunction of clauses with 3 terms. Now, let's assume that these are okay here, and we have the same thing there. So if this one is satisfiable, then at least one of the x's must have the assignment true. If this is satisfiable, there has to be a global assignment which assigns at least one of these to true. Now what we do is we introduce a new variable, u, and it's required that u not be used in any other part of the expression to the right or to the left. And the x1 and x2 are the same. So if our assignment gives the value true to either x1 or x2, then this clause is then assigned to be true, but then we assign u to be false, and then our second clause here is true. On the other hand, suppose the assignment we have makes either this one or this one, x3 or x4 true, then our clause here is true. We assign true to u, and we make this clause true. Therefore, this entire expression is satisfiable if and only if that expression is satisfiable. Let's look at a few things that are simple or more complicated. The clause x1 equals x2, the expression can be replaced by this conjunctive normal form, x1 or not x2, and not x1 plus x2. Try to convince yourself that that's equivalent to saying x1 equals x2. Likewise, x1 implies x2 could be written as not x1 or x2. Here's something a little bit more complicated. x1 equals the disjunction of x2 and x3. So this is or. So this would be x1 and not x2, or x1 and not x3, or not x1 and x2 and x3. That might be a little bit hard to see, but if you chase through all the possibilities, you'll agree that it's true. Here's an example of something slightly more complicated, where I found an equivalent expression using a truth table. X implies the disjunction of x2 and x3, and then I make a truth table here, and I discover that this expression is false in only one case, namely when x1 is true and x2 and x3 are both false. Now, I can then say the negation of that is this clause, not x1 plus x2 plus x3. Using the fact that Boolean expressions are generated by a context-free grammar, we can make use of that grammar to design a reduction of SAT to 3-SAT. we could use, let's say for example, we take a complex, a slightly more complex Boolean expression like this one. Now we could use a truth table for the variables x, y, and z to come up with a relatively simple conjunctive normal form equivalent version. Since there are only 3 variables, the truth table would only have 8 lines. However, suppose there are k variables in the expression, then the truth table would have 2 to the power of k lines, and that would go exponential as the size of the Boolean expression increased. Well, we need a polynomial space, polynomial time reduction of SAT to 3 SAT, and we make use of the grammar to do this. Now, starting with this expression here, I guess we could call this E if we want. Then we draw a parse tree for E, in which every internal node is assigned a new variable. And each of these new variables must be a name which does not occur elsewhere in the expression. So I'll just call those U1 through U5. Now, when we have a parse tree, we say that the value, we have to have an assignment on the leaves, which causes the value at the root to be true. So the first thing we say is that the root has to be true. Then for each internal node, the corresponding expression involving its children must also be true. So U2 must imply U3. U2 must equal U4 plus X. U3 must equal U5 plus Y. U4 must equal not Y. U3 must equal U5 and Y. U5 must equal not Z. Now each of these small clauses can be replaced by 1, 2, or 3 clauses of length no more than 3. And what this means is, in terms of the original expression, this thing that I wrote here has polynomial length. And then the corresponding 3C and F form also has polynomial length. So therefore we get a polynomial reduction. C321. What we have now is a polynomial time reduction of SAT to 3 SAT. Now 3 SAT is very clearly in the class NP. And SAT is known to be NP complete, although I have not indicated how that is proved. I plan to do that. And therefore, by the usual reduction theorem, we know that 3 SAT must be NP complete.